Algebra 1, Day 14. Today we're going to be talking about transforming linear functions. So we've already talked about how to graph these. Of course, we take our b value, our y-intercept, we plot it on our graph, and then we use our slope, our m value, in order to make additional points and create a line, and we connect them all, and they continue out forever and ever. But there's also a concept called transformation. So, for example, if I had two equations and I wanted to look at them and compare them, what their features would look like, I don't always have to graph them. What I can do instead is I can just look at the values in the equation, the m and the b, and I can determine what happens. These are going to be things like reflection, steepness or dilation, and also translation, sliding. And for these, they only have vertical shift, meaning up and down. So I'm going to show you guys a couple of things as far as calculator and a couple of other random things having to do with this. But first, I want to go ahead and get our notes out of the way. So let's take a look at our equation. Here, y equals mx plus b, this is slope-intercept form. Slope-intercept form. Now, my m is my slope, it could be positive or negative, and my b is my y-intercept. Tells me where it touches the y-axis. Remembering that my slope tells me what kind of change I have up and down, divided by what kind of change I have right and left for each and every point on my line. My y-intercept tells me simply where it touches the y-axis. So there's three different types of transformations that we're going to talk about today: reflection, dilation, translation. As you know, math people always make stuff super complicated, right? So I like to always use just plain words. Reflection, it's like a flip. Dilation, for this guy, is like how high. So is one side going to be higher than the other? And translation is going to be sliding. Okay? So reflection. First of all, the only thing that we have to know about reflection is that when my m is negative, the graph reflects or flips across the x-axis. So what does that mean? That means that all of my graph just changes places from where it was before. So let's go ahead and take a look at an example of that. So let's say that I have a random equation, 2x plus 6, and that'll be in blue. And now I'm going to mirror it. I'm going to take whatever my m value, this guy here, and I'm going to turn it into the opposite. So negative 2x plus 6. Noticing nothing else changed. Okay? So I could even say that if my original equation was negative 2, the mirror of it would be 2. Now notice, based on what we know already, these guys should have exactly the same y-intercept, so they should cross over each other. But they're going to be heading in different directions. All right, so if I look at my graph, I will notice that I have a blue line heading this way, my original line, a red line heading this way, my new line with a negative slope. Noticing that one has a positive slope, one has a negative slope. Now, if I look closely at this, I see a couple of interesting things. This and this are both the same distance from here. They meet here at my y-intercept, remembering that those y-intercepts were exactly the same, but the slopes were different. So that explains why one's heading in this direction with a negative slope, one's heading in this direction with a positive slope. If I go down a little more and I'm here at the origin, I can see same distance on both sides. So to me, this looks like this y-axis is acting like a mirror, because whatever's on this side is over here at an equal distance. Okay, so let's continue to fill this in. excuse me, that was not the x-axis, it was the y-axis. So, a dilation tells us about the steepness, okay? So, instead of just writing those in, let me go ahead and show you a few things about graphs. Now, noticing all I'm doing is changing the slope. I'm making it slightly bigger, okay? I'm going to take it way high, and then I'm going to go ahead and take it low. So I'm going to do it underneath 2. Okay, so now I'm going to go ahead and I'm going to turn off the ones that are less than 1, okay? First, we're going to focus on what happens whenever you increase the slope. So let's look at the graph. Here's my original line, okay? Slope is getting bigger. Slope is getting more bigger. Slope is getting way bigger. So if you notice, every time that slope went up, this side of the graph kept creeping up and creeping up. Okay, so if I think about this as like a mountain or a really tall hill, this one looks like it'd probably be a lot easier to climb than this guy. Meaning if my slope is higher, then it also means that it's steeper. That's way steeper. Now, let's go back for a second, and I'm going to drop in some negative. I want to see the same effect that this has when instead of having positive slopes, our slopes will instead be negative. Now, it's going to have the same exact effect, except it's going to look different, because remember, this mirrors it over the y-axis. So let's graph these. All right, here's my original one. Okay. Okay. So this looks exactly like the other one, except they're mirrored over the y-axis. Now, on this side, I don't think of this as the mountain, okay? I think of this as going downhill. So I would say -2 is more steep than -3, -4, -10. So, as you can see, it gets more steep on this side, but over here on this side, it gets less steep. Okay, so let's go back again. I'm going to go ahead, I'm going to get rid of that negative, and we're going to turn off all of these other equations, and I'm going to turn on the ones that are smaller than. So notice how my slope is going 2, 1, 0.5, 0.25. Let's graph it. Okay, here's my original one. Smaller slope, so look, it's getting less steep, less steep, less steep. All right, so it looks like whenever I bring my slope below 1, it gets less steep and it gets closer to being perfectly level. Now, just as a refresher, that perfectly level line would be a slope of 0. So 0x plus 6, which I can also write as y equals 6, okay? Let me just graph it. That's perfectly flat, right? This side's the same height as that side. So notice how my original line, as my slope went down and got closer and closer and closer to 0, it also got a lot more flat, okay? So, based on that information, let's talk a little bit more about dilation. So, when m is greater than 1, the graph is called vertically stretched and gets steeper, right? Because the mountain got harder to climb. But when m is somewhere between 0 and 1, such as things like fractions, decimals. The graph is vertically compressed and gets less steep. So you can think of that as getting like squished or flatter. So again, short way of saying it, m bigger than 1, it's going to get harder to climb. When m is somewhere in between 0 and 1, it's going to get more compressed as we go down. So if I go down, it's compressed. Also less steep. Okay, let's talk about these translations. So these translations are sometimes called vertical shifts. Let's go ahead and clear out all these. I'll just make this easy on myself. All right. So I'm going to go back. I'm going to type in a random equation. Okay, so 2.5x plus 6, right? So just some equation. Now, these translations are based upon not changing the slope from positive to negative, not changing the value at all. It's exactly the same. What changes is this b value. And I'm going to put in a couple of different ones so we can watch it shrink. And let's find out what happens. Okay, so I got a couple of values in there. Let's go ahead and graph it. So here's my original line. Okay, and then my next line went down a little, down a little, down a little more, and down some more. So it looks like every time I change this and go down, it drags my line down. Because if you notice, these guys all look like they have the same slope. They're all perfectly the same. It looks like somebody just grabbed the line, moved it down. They didn't change it. They didn't change the steepness. This didn't go up. This didn't go down, right? They just took the line and just bloop, slid it down. So what does that mean? Well, that means that based on that, we have vertical shifts, meaning up, down. Okay, so there's a little bit of an error here, so just follow along with me. So if b is bigger than 0, the graph goes up. Okay, so that's good. So if I add more to the y-intercept, it should go up. That makes sense, right? Because if I look at these, my y-intercept is going up. So if I add more to that number, the graph is just going to keep shifting up. Okay, so doesn't that mean that if b is smaller than 0, it's going to go down? Okay, so now we have so much information. So the way that we usually talk about these is we usually compare them to what's called the parent graph. So the parent graph looks like this. That's how you usually see it. But I like to write it out like this, so that way you see it has a y-intercept of 0 and a slope of 1. Okay, so let me go ahead and look at this one, and I'm going to say my parent graph looks like this. Okay, so based on those rules that I saw earlier, I'm going to do the easy one. I see this is a plus 2. That's 2 more. So it went up 2. Okay. All right. So now I'm going to look at this slope. So it looks like that negative number here would tell me that it reflected on my y-axis. And the 3 tells me it's steeper. It's going to go up. Okay. So let's go ahead and plot these two. So I'm going to go ahead. I'm going to clear out everything all over again. I'm going to go back to this. I'm going to plug in my parent graph, 1x plus 0, the guy that we're comparing it to. And now I'm going to plug in their graph. And let's see how they compare. Blue is going to be my original. Red is going to be what they changed it to. Okay. All right. So it looks like I made a pretty good prediction. They moved 1, 2 up. It flipped it over the y-axis, so that was the negative. And then look at that. This side is way higher than that side, right? It looks like this would be way more difficult to climb. So that means that this line is less steep than this line. Okay. So let's go ahead and write in a couple of those things. So this is most certainly reflected across the y-axis. And this is steeper, right? Vertically stretched by a factor of 3, because 1 times 3 is 3. And it's translated up, not down, 2 units. Okay. So the graph of f of x equals x is the parent function. All right. So let's go ahead and take a look at what this graph looks like. This is our practice for graphing, okay? So first thing I'm going to do is I'm going to locate my y-intercept. I'm going to go ahead and plot it here on the y-axis, remembering that my y-axis runs up and down. My x-axis domain runs side to side. Now I'm going to go ahead, I'm starting at that point, I'm going to use my slope, n equals -3. But remember what I told you, this has got to be a fraction. So I'm going to say -3 over 1. So I'm going to go 3 down, 1 right. So 1, 2, 3, 1 to the right. 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 Okay, so now I'm going to do the same thing again, but I'm going to do in the opposite direction. And since I'm doing opposite, I'm going to do 3 up, 1 to the left. 3 up, 1 to the left. And I've run out of room. So I'm going to go ahead and connect all of my dots, draw some arrows in case anybody's suspicious my line doesn't keep going. And there's my new line. So this line is incorrect. That is not f of x equals x, because look at that. It's got a y-intercept of somewhere around 1. That's totally not it. So we're just going to ignore that. All right. So let's take a look at this guy. Oh, we forgot to plug in our values. So for this one, remembering that we can also take a look at our table. So I'm going to go ahead and delete this. I'm going to hit second table just to verify my values. I'm looking for x equals -2. So that's going to be 8. I'm looking for my y-intercept is 0, 2. And x equals 3, -7. All right. Of course, I could have also plugged those numbers in, but just to keep our video short, I'm not. All right. Let's do the same thing over here. So I'm going to go ahead and zoom into my equation. I see that, of course, I'm going to be comparing it to this guy. Okay, so obviously that's a -3. 3 down. Okay, and this 1/3, that's smaller than 1, but still bigger than 0, right? So that's going to be a vertical compression. We're squishing it. You could also say that it's less steep. Okay, so let's kind of answer these questions. Is this reflected across the y-axis? No. Is it vertically compressed? Yes, by a factor of 1/3. Is it vertically stretched? No. Is it translated? Yeah, 3 units down. Okay, let's go ahead and graph this. First thing I'm looking for, let's going to be my y-intercept. So I'm going to look for that here on my y-axis, -3. I'm going to take my slope, m equals 1 over 3. So it's going to be positive 1, 1 up, 3 right. So 1 up, 3 right. And I'm going to keep doing that until I run out of graph. In the opposite direction, I do the opposite. Down 1, right 3. Down 1, right 3. Down 1, right 3. Now that I have a full graph of points, I'm just going to go ahead and draw my line, including my arrows, just in case anybody gets suspicious about my graph continuing on. Notice that if these were mountains, the black line, which actually is y equals x, that's what it looks like, would be much steeper, harder to climb. The red one, on the other hand, would be less hard to climb. So, I want you guys to go ahead and take a look at these and do your best to answer them, and I will see you next time.